The Collatz conjecture is one of the most famous unsolved problems in mathematics. The conjecture asks whether repeating two simple arithmetic operations will eventually transform every positive integer into one. The algorithm goes like this. Given any positive integer, if the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Repeat the process and, eventually, the sequence will converge to 1. Let's see an example, starting with the number 12. 12 is even, so we divide it by 2, resulting in 6. 6 is even, so we divide it by 2, resulting in 3. 3 is odd, so we multiply it by 3 and add 1, resulting in 10. 10 is even, so we divide it by 2, resulting in 5. 5 is odd, so we multiply it by 3 and add 1, resulting in 16. And now we'll have a sequence of divisions that goes 8, 4, 2, 1. Note that when the sequence hits a power of 2, it's fated to decay to 1. Simple, right? But it's not that simple. I started to work on this problem after watching a video from Veritasium. I invite you to go and see that video. I've left a link to it on this video's description. I'm sure this content will make more sense if you check that video first. In this video I'm going to try to answer two questions. Is there a number that makes the sequence grow forever? Is there a number that makes the sequence enter a loop? I can assure you the answer for both questions is no. Which leads me to assert the Collatz conjecture is actually true. And I'm going to show you why. But, in order to do that, I'll have to use binary notation. Yes. I know people already tried to extract something from 3n plus 1 in binary. But I believe they have not noticed some subtleties, which I'm going to cover here. Now let's see what 3n plus 1 looks like in binary using the same example, starting with the number 12. 12 is even, so we shift all bits to the right one spot. In binary, this is the same as dividing by 2, and we get 6. 6 is even, so we shift all bits again, resulting in 3. 3 is odd, so we multiply it by 3 and add 1, resulting in 10. 10 is even, so shift the sequence to the right, which will give us 5. 5 is odd, so we multiply it by 3 and add 1, resulting in 16. And now we'll perform a sequence of right shifts, like this, getting to our final result, 1. One important thing to notice here is that when we divide by 2 the pattern of the bits do not change. Just their spots. And every time we perform a right shift, the number of bits in the sequence shrinks. On the other hand, when we multiply by 3 and add 1, we actually change the pattern of bits, and the number of bits in the sequence grows. And when I say shrinks and grows, I'm actually referring to the amount of bits from the most significant to the least significant one. This becomes a little easier to see if we remove the leading zeros, like this. Now, notice how the size of the sequence changes after each step of the algorithm. And, from this point forward, we are not going to think in numbers. We are going to think in bit sequences, and how many bits it contains. And whenever I use the term full cycle, what I mean is the interval from one odd number to the next. And when I state the sequence will shrink or grow a certain number of bits, I mean the difference in length from the odd number at the start of the cycle to the one at the end. The longer the number we have to represent in binary, the more bytes we're going to need to fit our bits. And the reasoning I'm going to show you is actually valid for any sequence of bits, of any size. To understand what 3n plus 1 actually does, we're going to look at half a byte at each end of our bit sequence. Half a byte is called a nibble. The least significant nibble is the one at the right end of the sequence. The most significant nibble is the one at the left end of the sequence, and it must have, at least, one lit bit. If the most significant bit is at this half of the byte, I'm going to take it as the most significant nibble. If the most significant bit is at this half of the byte, then this will be the most significant nibble. The least significant nibble dictates how the sequence shrinks. The most significant nibble dictates how the sequence grows. The sequence shrinks after we multiply it by 3 and add 1. And the sequence grows when we multiply it by 3 and add 1. We know it's time to multiply by 3 and add 1 when this bit here is lit. When we multiply by 3 and add 1, the sequence may grow 1 or 2 bits, and only 1 or 2 bits. If it grows 1 bit, it will be like this. If it grows 2 bits, it will be like this. And we'll always count the size of the sequence from the most significant bit to the least significant one. Now let's see what happens to the least significant nibble after each step of the algorithm. Imagine we have a very long sequence of bits. What's to the left side of this nibble doesn't matter. It may be anything. If the nibble is like this, all zeros, then we're dealing with an even number, which we must divide by 2. So, we know the entire sequence will shift one spot to the right. And whenever we shift the sequence, the bit just next to the nibble will enter into its most significant spot. It may be a 0 or a 1. If it's a 0, the nibble's appearance will not change. If it's a 1, then we're gonna have this. We still have 3 shifts to perform. On the next shift, another bit will enter the least significant nibble. It may be a 0 or a 1. So, the nibble may become this. Or this. By following this process, we can trace what the least significant nibble may turn after each shift, until we reach the next odd number. And now we multiply the entire sequence by 3 and add 1. Unlike what happens when we divide by 2, the pattern the nibble will assume when we apply 3n plus 1 is fixed. Each configuration in red will turn into the one we see in gray. Notice that the top half of our branch always leads to consecutive divisions. And each gray pattern corresponds to a white pattern. This one, for example, will restart this path, and the next shift may bring us to the same final configuration. But it can also lead us to this one, which loops to this node. This one will loop to the top half of our branch, leading to consecutive divisions. And this one will do the same. It's like 3n plus 1 actually wants to perform consecutive divisions. Half of the times, after applying 3n plus 1, we'll shift the sequence right 1 time. A quarter of the times, we'll shift the sequence right 2 times. An eighth of the times, we'll shift the sequence right 4 times. And the last eighth of the times, we'll shift the sequence right 3 times. Now let's see what happens with the other end of the sequence when we apply 3n plus 1. The most significant nibble is a little bit harder to tame. There are 15-bit patterns we must consider. And when applying 3n plus 1, we must take into account a neighbor bit, which can be a 0 or a 1. And we also must account the chances of a carry bit to be propagated into the most significant nibble. Accounting for all these things, we'll end with 60 possible resulting patterns. I'm not going to show you the 60 possible resulting patterns for the 3n plus 1 phase of the algorithm on the most significant nibble here. But I've left a link to a spreadsheet down there in the video description. You may check it later, if you want. Despite all the fuzzy stuff here, one thing is for sure. When we multiply by 3 and add 1, the sequence will grow. It may grow 1 or 2 bits. And only 1 or 2 bits. If it grows 1 bit, it will be like this. If it grows 2 bits, it will always be like this. A 1 followed by a 0. And these gap bits here are important, because they'll slowly set the stage for the bit grinding this algorithm performs. This table shows what happens to a bit sequence after 3n plus 1 is performed over it. When we multiply by 3 and add 1, the sequence will grow 2 bits 2/3 of the time, and grow 1 bit 1/3 of the time. But, as we've seen before, after we apply 3n plus 1, we'll perform 1 or more divisions. So, every time the sequence grows 2 bits, it will shrink at least 1 bit right away, half of the times. The net result of a full cycle, from one odd number to the next, is shown here. Note that there is only one crossing point in this table that shows the sequence will actually grow after a full cycle. All the others show the sequence will remain the same size, or shrink. Doing the math, we get this. After a full cycle, the sequence will grow 1 bit 1/3 of the times. It will stay the same size 1/3 of the times. And it will shrink 1/3 of the times. Simplifying things a bit, we have this. Note that this shrinking third here will remove slightly more bits than its growing counterpart up there. And that's why any bit sequence will always tend to shrink instead of growing forever. The sequences that peak higher, that is, the ones which grow more, are the ones having big chunks of consecutive ones in their pattern. But every time the sequence grows 2 bits, which is 2/3 of the times we apply 3n plus 1, a gap bit will be added next to the most significant bit of the result. And that gap will make the difference in further steps of the algorithm, breaking those chunks. Now, the infamous loop. This is the second question this video wants to answer. The only known loop in this algorithm is when we choose the number 1 as our starting point. 1 is odd, so we multiply it by 3 and add 1, getting 4. 4 is even, so we divide it by 2, getting 2. 2 is even, so we divide it by 2 again, getting 1. 1 is odd, so we multiply it by 3 and add 1, getting 4. And the thing repeats forever. If the algorithm had a check for the halt point at the beginning, as we usually do in programming, there would be no loop. Because if you picked 1 to start with, then you're already at the halt point. And then we'd have no loop at all. Now let's suppose there are other loops besides 4 2 1. Then I'd be able to pick a bit sequence that, after applying the rules of the algorithm a certain number of times, would generate a pattern that would lead to the one I started with. Remember that the only step of the algorithm that actually changes bit patterns is the one where we multiply by 3 and add 1. Now let's try some backward thinking. This last pattern here must be the result of multiplying something by 3 and adding 1. And we know that occurs only for odd numbers. Is there an odd number which can generate the pattern we want? Yes. This one. Okay, so we got the closest ancestor. Now let's go up one step. We know the closest ancestor was the result of a division, so it should be like this, one step before. Now, is there a pattern that can generate this one? I dare you to find an odd number which could. In order to generate the desired pattern, we'd have to perform 3n plus 1 over an even number, which is not allowed by the algorithm. And that's why there are no loops. They're not possible. Pick any pattern you want and try it backwards. You'll see that it's impossible to get to it, because in order to do that, you'd have to apply 3n plus 1 over an even number at some point, and that's not allowed. Half of the odd patterns in the integer universe are unachievable through this algorithm, and they'd be needed in order to allow a loop to occur. 3n plus 1 is a bit grinder. And this bit, right here, is Highlander. It's the only one the algorithm is unable to delete. I don't know if what I'm showing here counts as a proof. Actually, I don't even know what a mathematical proof looks like. But if this can lead someone on the path of a formal proof, so be it. I'll be happy with that. And if that someone is you, please, don't forget to mention where the idea came from. Thank you.